conformal field theory in 2 dimensions to relate familiar structures such as within the algebra with interesting geometric objects such as the moduli space of flat connections on a Riemann surface. So this time we will move into a higher dimension. We'll consider 4-dimensional conformal field theories, and we will generalize this relation between we'll generalize this relation to a new relation between what's known as the equivariant within the algebra. This is a 1-parameter deformation of the familiar within the algebra with the geometry of the moduli space of complex flat connections. And also we will look at class of closely related moduli spaces. Those are moduli spaces of wild Higgs bundles. And we will discover some hidden algebraic structure, such as model tensor categories, or even better, families of model tensor categories. So both the moduli space of complex flat connection and the moduli space of wild Higgs bundles are examples of Coulomb branches of 4-dimensional quantum field theories. So maybe let me start by telling you more precisely what do I mean by Coulomb branch of 4D quantum field theories. So the quantum field theory that we'll be dealing with has supersymmetry. So they are for the n equals 2, and n equals 2 is referring to the amount of supersymmetry that it has. Supersymmetric theory. And for any quantum field theory, let me denote it by curly T. You can consider that a 4 manifold. And then ask, what is the moduli space of lowest energy configurations? Or what is the moduli space of vacua for this theory? And in general, the moduli space of vacua could have different components, and the structure of this can be quite intricate. But for the n equals 2 theories, there is a particular component of the moduli space of vacua known as the Coulomb branch. Since it will be the focus of this talk, I will just denote it by MT. And the entire moduli space could look roughly like this. So we will have a Coulomb branch. And then there can be other branches, such as Higgs branch, and possibly some branches that sit in between Coulomb and Higgs branch, known as mixed branches. So the entire model space of vacuum is expected to be hyperkähler, and in particular, the Coulomb branch is also expected to be hyperkähler. This means that it emits a hyperkähler metric and 3 independent, compatible complex structures. And in this case, there is a canonical choice of the complex structure I. So it's some complex structure that is somewhat special. And there is also going to be 3 Kähler forms. Denoted as little omega I, little omega j, and little omega k. And hyperkähler manifold is also holomorphic symplectic in many different ways. So there are 3 corresponding holomorphic symplectic forms denoted as capital omega I, capital omega j, and capital omega k. And in this special complex structure I, MT, it has a very nice structure. It will be a complex integrable system. This means that it emits a vibration over a base with fibers being generically complex Lagrangian tori. So to give, well, this space also has some other interesting properties, but maybe it's a good idea to first give you a very simple example. Perhaps the simplest non-trivial Coulomb branch is a Coulomb branch of the U1 gauge theory. So this is a free theory. So one can perhaps also refer to this theory as free theory of rank 1. And the Coulomb branch of this theory looks like the following. The base of this vibration, B, will be one-dimensional and will just be the complex plane. And this family of complex Lagrangian tori will be, this vibration will be trivial. So entire space will simply be the product of an elliptic curve and the base C. And this, the convex structure on this T2 is fixed by some data that define the U1 gate theory. As many of you know, gate theory, when you are trying to define a gate theory, you need to choose some data such as coupling constant. And there's another parameter known as theta angle. If you combine them, you can view that you can view this U1 gate theory as being labeled by an elliptic curve E or sigma. This is an elliptic curve, and this T2 can be identified with a dual of this elliptic curve. This can be generalized.
And what is the corresponding integrable system?
Well, this is already a classical integrable system, but it's kind of trivial. The vibration is trivial.
But the fiber is torus. Why it's trivial?
You are not having so trivial in the sense that this vibration is trivial, and also, well, in a sense, dynamics of integrable system is always trivial since it's because it's integrable. But in this case, the vibration is trivial. I hope this is what you are asking.
Sorry, I don't understand, because I thought that if you have one-dimensional torus as a layer, as a fiber, then you have some non-trivial integrable system, one-dimensional.
So here, as an integrable system, perhaps you can refer to it as a non-trivial one. I certainly agree with this. Here, trivial just means that geometrically, this family of torus give you a trivial vibration. So this is a direct product instead of having something more interesting.
Yeah, okay, but in this trivial case, what is the system? I mean, dynamic. Which system governs the dynamic of the system?
Oh, for example, if you can consider motion of particles. So, well, on the base. So, in general, for such an integral system, this vibration is given by set of Poisson commuting Hamiltonians, right? And you can generate a Hamiltonian flow using any of them.
Yeah.
So in this,
I thought that if the base is one-dimensional, that means that there is one Hamiltonian.
Yeah,
yes?
Yeah, exactly. You can still generate flow using it.
Okay, and this is Hamiltonian of what system? Because there is a lot of different systems with one Hamiltonian, and all are integrable. Or probably this is incorrect question. I don't know.
So this is a complexification of the well, the Hamiltonian that generates motion of particle on well,
for example,
literally the circle, right? This is a complexification of this.
For example, I want to try to explain what I mean, because, for example, I heard that to SU2 gauge theory in n equal 2, we have to the chain with two particles.
That's the quantum integral system that corresponds to this. Here, I'm just talking about classical integral system.
Yeah, classical to the chain. I mean, to the lattice. I don't know.
Well, I think that's like a different sort of correspondence. So here I'm just referring to the geometry of the Coulomb branch.
Okay.
So it has the geometry of a classical inverse system, but there are often ways to get more interesting, either quantum or more interesting inverse systems.
So this is different Coulomb branch, not those which I asked about.
It's the same Coulomb branch, but there are different relation to inverse systems. And here, the geometry of Coulomb branch itself is an inverse system, but in the classical sense.
Okay, thank you.
No problem. So please feel free to ask any questions. And there is a generalization of this to free theory still, but of higher rank. And then topologically, this space just looks like indeed 3 copies of C times T squared. So it looks like the following. The base is a product of 3 complex planes. And then you have an abelian variety that is also 3-dimensional. And the fibration is again trivial. Similar to the Rank-1 case, you can label a family of such theories using a Riemann surface with genus G. And the fiber can be identified now with the Jacobian of sigma. And the entire space can be identified with the total space of the cotangent bundle to the Jacobian of sigma.
I'm sorry, but these examples for what? For S1 times R3 or?
Yeah, so the moduli space MT is always for the always denote the Coulomb branch on S1 times R3.
Okay, what do you mean by labeled by Riemann surface?
So like in the first example, to specify the U1 theory, you need to specify some additional data like coupling constant and then theta angle. And the story is similar here. Now you want to specify some additional data that can define for you the U1 to the G gauge theory. And there is a particular set of data that can be packaged together to the complex structure of a Riemann surface. So for a Riemann surface, you have the period matrix, and that you want to identify that with a coupling matrix for the U1 to the G gauge theory. Does this answer the question?
Yes, thank you.
So since SU2 was mentioned, let me maybe talk briefly about the SU2 gauge theory. In the previous 2 examples, the fibration is trivial, but you certainly won't expect that this is true for the SU2 gauge theory because it's interacting theory. It's no longer free. In this case, MT is sometimes referred to as the Seiberg-Witten geometry. The base is still 1-dimensional, but now there are 2 special fibers over these special fibers. So over these two special points, the fiber become degenerate. Away from these two special points, again, you have a smooth elliptic curve. And if you go around these two special points on the base, you pick up SL2Z monodromy. So in this case, the monodromy will be given by this particular elements in SL2Z and this one. So now you have a non-trivial family of a non-trivial elliptic fibration. So, of course, you would expect that this theory has more interesting dynamics compared to the previous two examples. But actually, example 1, 2 enjoy a special property that the third example does not have. On the moduli, on the moduli space on the Coulomb branch, for the example 1, 2, you have a U1 isometry that acts in the following way. On the base, it will just be a jotation. In the second example, in principle, you can define many such U1 isometries, and you can pick the diagonal one. But in this example, you cannot find a similar U1 isometry. So although the example 1, 2 looks simple, it enjoys special symmetry that the third example does not have. And this particular U1 isometry is related to conformal symmetry. And in the rest of this talk, we'll also be focusing on conformal theories in 4 dimensions, since they enjoy both supersymmetry and conformal symmetry. They're often referred to as superconformal theories, or SCFTs. So for such theory, MT would enjoy an action of U1 that preserve the hyperkähler metric, and it further has a property that the only fixed point on the base so it only fixes special points on the base B, and that's special points. I will denote that by O, and this is often referred to as the superconformal point. And this U1 action also has other special properties. For example, it's compatible with the fibration onto B, and that's it's a hidden assumption that is used to state this property. It also enjoys some other nice properties that I don't want to state for now. So to give a non-trivial example that is superconformal, one can again look at non-abelian theories but with some matter. The class of such theory that give you a non-abelian generalization of the second example is the class of theories of class S. And they are labeled again first by a genus G Riemann surface, possibly with some marked points, with some ramification data associated to each marked point, and then compact Lie group G. This is often assumed to be of type ADE. But ADE won't play a terribly important role in this talk. And indeed, if you take G to be U1, you will recover U1 to the G gate theory, the second example. So the Coulomb branch for theory of class S can be identified with the moduli space of GC Higgs bundles on sigma. And there are different ways of looking at the same moduli space. For example, one can identify this space with the Hitchin moduli space. Denoted as MH sigma G, and this is defined to be moduli space of solutions to a set of PDE known as Hitchin equations. Quotient by some gauge transformation. And this space can also be identified with the moduli space of flat complex GC connections. On sigma. So in the first lecture, we have already seen a close cousin of this. Indeed, the moduli space of flat connection, flat G connection, sit inside this moduli space. So to give a more concrete example, let's take G to be, again, SU2, and G, the genus of the Riemann surface, to be 2. Then the base of the vibration is going to be 3-dimensional. So it's hard to draw compact 3-dimensional thing on the board. So I will just draw it like a complex plane. But then there is a special point, this super conformal point, that is fixed by the U1 action. And the fixed points of this U1 action on the entire space sit in the fiber over the special points O. And they have the following structure. Again, you have the familiar CP3 moduli space of flat connection, a flat SU2 connection on a genus 2 Riemann surface, sitting inside the fiber over O. And then there are additional 16 points that are also fixed by the U1 action. So the fiber over O is basically the union of CP3 together with all the downward Morse flows from these 16 points. So last time we have seen an interesting connection between geometry of CP3 with the Berliner algebra associated with SU2. For example, if one compute the following integral on CP3, one recover the Berliner formula for this genus 2 surface. Given by this polynomial in K, and this can be identified with the dimension of the space of homomorphic sections of the line bundle OK on CP3. And this can also be identified with a partition function of a 2D TQFT on sigma. Now, natural question is that can one complexify this formula? What do I mean by complexify? Well, here, for this space, for the one can try to replace, replace CP3 or the moduli space of flat connection with a Hitchin moduli space. And then OK will be replaced with K's power of a special line bundle, L, sometimes referred to as the determined line bundle, over MH. This line bundle, again, have trivial higher cohomology. And the any question? No. So the space of homomorphic sections again can be identified with the geometric quantization of the Hitchin moduli space MH. So by complexifying, we're trying to find the answer to a very interesting problem, like what is the Hilbert space of that you obtain after quantizing the Hitchin moduli space, and how to better understand it. But since MH is not compact, this space is expected to be infinite dimensional. So it does not make sense to compute the dimension of this. But since this space enjoy U1 action, and this line bundle is also equivariant with respect to this U1 action, we'll actually have a U1 action on this infinite dimensional vector space. So instead of computing the dimension, one can compute the graded dimension or the character of this U1 action on this infinite dimensional space. And that turned out to be well defined. And this is because the U1 action on MH, the fixed point of this U1 action is compact. So because the higher homology vanish, one can identify this the character of the U1 action with the equivariant index of this line bundle over MH. And one can introduce a parameter T to keep track of the equivariant parameter. And this equivariant index would take the following form. The constant piece will be exactly the usual index of L to the K on the model space of G connections, or equivalently, the model space of semi-stable homomorphic GC bundle on a Riemann surface. And then there are corrections in the example of CP2, we would have well, let me just write chi t will equal to this piece for the constant term, and then a term that looks like this. In front of t. And something like this in front of t square plus dot dot dot. And one can actually try to sum this up, and then one can identify the contribution from CP3 and the 16 points. Indeed, such equivariant index can also be written as an equivariant integral over the entire space. And one can apply localization theorem to this integral and break this into sum over components of the fixed point sets. And one can actually separate contribution from CP3 and contribution from the 16 points. But what's nice about this kind of objects is that, again, it's going to be a partition function of a 2D TQFT. So there is a one parameter deformation of this 2D TQFT whose partition function captures this equivariant index. Therefore, you can study geometry of complicated Kitchen model space simply by cutting and gluing on the TQFT side. To make this explicit, recall that for G equals SU2, the Verlander formula or the Verlander algebra is controlled by, it's given by the following data. You have a vector space that has dimension k plus 1, and it's spanned by these basis vectors E0 through EK, and the label correspond to integrable height weight of SU2 at level K. And then you have this bilinear pairing specified by eta. And the fusion coefficients. And the fusion coefficients is only allowed to be non-zero when the sum of lambda is even, and when this function that I defined last time is smaller or equal than 0. So recall that nice way to visualize the fusion coefficient is by looking at the space of lambda 1, lambda 2, lambda 3 triple. So they are they take value inside this cube. Integral points inside this cube, and the fusion coefficient can only be non-zero if the point is even, and further if it lives inside a tetrahedron. This is the blue one here. And this delta is measuring the distance between the point lambda 1, comma lambda 2, comma lambda 3 to the tetrahedron. So this smaller than 0 means that it's in the interior of the tetrahedron. And the one parameter deformation is given by first deforming eta to be the following. It's still diagonal, so it will be delta lambda 1 times lambda 2, but now times a constant that depends on lambda. It can be either 1 over t, sorry, 1 minus t, or 1 minus t squared. 1 minus t squared if, let me write it maybe in opposite order. 1 minus t squared if lambda equals to either 0 or k, and 1 minus t otherwise. And the fusion coefficients will also be modified. Now, when you are outside the tetrahedron, you are also allowed to have a non-trivial f. And it will be t to the delta power. And now it's not entirely obvious that after the deformation, this is actually a Frobenius algebra. But what is obvious is that if I take the t equals to 0 limit, indeed one would recover the familiar Boolean algebra. And it's a non-trivial fact that in general, it defines commutative Frobenius algebra then it also solves the quantization problem, or more precisely, compute the graded dimension of the Hilbert space after the quantization of MH. So here I've given this for this equivalent algebra for SU2, but this can be generalized to all simple tree, simple and simply connected. So we first explored this with Sergey using physics. But then most of the prediction coming out of physics has been proved using algebraic geometry in the work together with Jon Anderson. And one expects that just as Boolean algebra is closely related to rational CFT, we expect that this story is related to some irrational conformal field theories. But if the CFT is irrational, then you should not expect that it can be lifted to a 3D TQFT, which is controlled by a model tensor category. Indeed, there can never be such thing as a continuous one-parameter family of model tensor categories because of rigidity, as Victor has mentioned yesterday. So it's inconceivable that this family of 2D TQFT can be lifted to a usual 3D TQFT controlled by a model tensor category. So now we will try to ask a question that whether it's never possible to get something like model tensor category from Coulomb branch for any theory. And if this is possible, what kind of condition that you want to put on the theory and how to construct such model tensor categories. One can actually get quite close. It turns out that for any hyperkähler manifolds, such as MT, one expect to have a braided ribbon category. This is a braided tensor category satisfying some additional constraints. One expect to get such a category by considering the Rosansky-Witten model onto this model space MT. So what do I mean by this? Rosansky-Witten model is a special kind of 3D theory that is a fancy version of a 3D sigma model. Recall that for sigma model, the basic degree of freedom is a map from the 3 manifolds to the target space, and then the path integral is given by integrating over all possible maps and weighted by a particular functional of phi. And the Rosansky-Witten model is basically a fancy version of this. The degree of freedom involves this phi, but together with some other fields. Some of them are fermionic. And we'll also integrate these additional fields here. And the action functional will also depend on these additional fields. So the Rosansky-Witten model is expected to be topological, but it's not expected to be 3D TQFT in the usual sense. This is because sometimes the partition function is not well defined. So for many M3, even for very simple ones like the 3-sphere or length space, when the target space MT is not compact, the partition function formally will be infinite. And the dimension of the Hilbert space of Rosansky-Witten model on a Riemann surface, again, is often infinite. Then it seems that there's no hope of obtaining a model tensor category out of it, because anything that you can construct from an MTC would necessarily have all partition function well defined and all the Hilbert spaces finite dimensional. But just as we can regularize the dimension of the space of holomorphic section of this line bundle over the Hitchin model space, one can ask whether one can again regularize these infinite Rosansky-Witten partition functions. Again, using the U1 action on the Coulomb branch. It turns out that it's okay, one can attempt this, but for special three manifolds, such as Seifert three manifolds. A particular Seifert manifold is a length space LK, 1. This is a quotient of S3 by finite group ZK. And it turns out that this particular partition function can be indeed regularized using the U1 action. After regularization, one would introduce an additional parameter t, and this can be exactly identified with the equivariant index of the line bundle L to the k. So this is, again, this quantity that the equivariant within the algebra can be used to compute. But certainly you should not expect that this procedure will work for more granular M3. Otherwise, you would again have a one-parameter family of MTC that is not allowed. And one way to see that the regularization using U1 is problematic is by noticing that U1 actually acts on hyperkähler structures. So the U1 is homomorphic in compact structure I, but it will rotate compact structure J into compact structure K. So it will change the hyperkähler structure of this Coulomb branch. But Rosansky-Witten model, to define it, you need to actually specify the hyperkähler structure. So there's some intrinsic conflict between this U1 and then topological invariance of Rosansky-Witten model. So you shouldn't expect that you can use this U1 to regularize the entire Rosansky-Witten model unless you are on some special three manifolds. But this does not mean that you cannot do anything. But one way to avoid this problem is by looking at subgroup, finite subgroups, a finite subgroup of U1, such that it fixes the hyperkähler structure so then it will be compatible with the 3D Rosansky-Witten model. And then to use it to regularize, one further require that the fixed points of ZF is again only consists of the superconformal points. If these two conditions are satisfied, then you expect that the resulting Witten model, for example, let's say on again dense space, can be regularized by picking by again using this formula, but specialized with T specialized to F's root of unity. So one should use, well, one can use any primitive root of unity, and it's, this function will be regularized and take value in this field. So we will try to use additive notation, and we'll write this primitive root of unity as exponential of 2 pi I gamma over F. And gamma is represented by an integer that is co-prime with F. So for this, it seems that one can use such a subgroup of this to regularize at least partition function on dense space. And the conjecture is that this procedure can be used to regularize partition function on any three manifolds, and it actually gives MTC. So this is in joint work with Nicola Dodchenko and Sergey, Hirako Nakajima, and Cuellar. Conjecture that one can actually get a family of model tensor category, MTC, C, well, subscript T, and gamma. And one also expect there is a nice dictionary between geometry of MT and algebraic structures of the model tensor category, at least for gamma equals to 1. This is because, for example, for such quantity, one can compute this by performing equivariant integral, and that depends on geometry of the Coulomb branch. But one can also compute that from data, using data of the model tensor category. So therefore, one expects that there is a dictionary between geometry of the Coulomb branch and the data for the model tensor category. So the dictionary is the best understood when gamma equals to 1, but one can easily get other gamma by performing a Galois transformation on the model tensor category. specified by an element in ZF star. But all of the above rely on the assumption that this number f is larger than 1. Otherwise, ZF will be the trivial subgroup, and one certainly shouldn't expect that one can use it for anything. So can f actually be larger than 1? Is there a theory such that there is a non-trivial subgroup inside the U1 that fits the Herbert-Kähler structure? The answer turned out to be yes. And one particular class of theory that has this property is known as generalized Algebras theories. So they are close cousins of theories of class S, but instead of being labeled by a Riemann surface, they are labeled by sigma that is fixed to be CP1, but with a special point where you can have a higher order pole for some of the fields. So the modular space can be identified with either the model space of wild Higgs bundle or equivalently wild Hitching space, a wild Hitching modular space. Which is defined as, again, solutions to Hitching equations, a set of PDEs on the Riemann on CP1, but with some of the field developing higher order pole near the special points. There can be an additional point where you have a regular pole. You have regular pole at one point, and then a higher order pole at another point. Again, you quotient by gauge equivalence. So to give some very concrete examples, so a class of Algebra theories is labeled by a pair of ADE Deacon diagrams, and the simplest one is the A1, A2 theory. The next simplest is perhaps A1, A3, and then A1, D4. They have the nice property that the modular space of Hitching, well, the wild Hitching modular space is one Herbert-Kähler dimensional. So they again all have the structure of elliptic surfaces. So B will be one dimensional. It can be identified with a complex plane But then there is going to be a special point, the superconformal point. And for the A1, A2 theory, the fiber of this point look like this. So this singularity of this of elliptic fibration is known as type 2 singularity in Kodaira's classification, or affine A0 singularity. For the other two moduli spaces, it's very similar, but the fiber will be respectively having type 3 singularity or type 4 singularity. So the action of U1 would have some fixed points, and in such cases, they're necessarily isolated. In this example, there are going to be 2 fixed points and 3 fixed points in this example, and 4 fixed points in this example. And the U1 fixed points will, of course, be exactly also the F fixed points. So F, this particular number, will be 5 in this case. This means that there is a Z5 subgroup of U1 that is special. It will preserve the hyperkähler structure. And F equals to 3 and 2 in the A1, A3 case and A1, D4 case. So F, from the point of view of Wald-Hitchin spaces, is basically telling you that there is some interesting Stokes phenomenon when you are solving these PDEs around the higher order pole. So there are going to be some Stokes rays. And F is roughly total number of Stokes rays. So let's take one of this moduli space, and I will describe for you what is the dictionary between geometry and algebra. So let me maybe try to draw this. To zoom in. So this is a bigger version of the singular fiber. So we expect that fixed points of the U1 action would correspond to equivalence class of simple objects. So on this side, it's about geometry. On this side, it's about the model tensor category, CT gamma equals 1. And then, since the U1 action is actually Hamiltonian action, is generated by a moment map, one can talk about the value of the moment map at each fixed point. And this value can be translated into value of the T matrix. So in the basis given by simple objects, the T matrix is expected to be diagonal. And this is basically this quadratic function Q that Victor mentioned up to overall shift. So in this particular example, the T matrix will take the following form: be e to 11 pi I over 30, e to minus pi I over 30. Well, and for the MTC, one important data is the S matrix. So how to get this S matrix? It turns out that the data for the S matrix is encoded in the weights of U1 action on the normal bundle to fixed points. In this example, the S matrix will take the following form. So some of you may get concerned about the minus sign for this entry. Indeed, for any unitary model tensor category, you should expect that you have a positive 0,0 component. But it turns out that this category is the Li-Yang MTC, which is non-unitary. This MTC is also known as the 2,5 Virasoro minimum model. So if you still remember the formula for central charge of the Virasoro minimum model for any P, Q minimum model, you can compute it, and you will find that the central charge equals to minus 22 over 5. So the conformal field theory is expected to be non-unitary, and also the model tensor category is non-unitary. How about other gamma? In this case, f equal to 5. So gamma can be 1, 2, 3, or 4. When gamma equals 1, you get the Li-Yang MTC. And when gamma equal to 4, you get the complex conjugate of the MTC. And I think in Victor's notation, this is perhaps should be denoted as the reversed. And for gamma equals to 2, you get a Galois transformation of the MTC. And then it will turn out to be a unitary model tensor category, because Galois action does not preserve unitarity. The unitarity condition is not algebraic. For gamma equals 3, you get something again somewhat familiar at 4 at level 1. So behind this model space that looks fairly simple, you can actually find some interesting model tensor categories. And you can check this for much bigger class of theories. We can check the dictionary, which is not yet complete, since there are more data for the model tensor category. For example, one important data is the fusion rule, and also braiding captured by the R matrix, and the associator captured by the F matrices. We have some understanding about the fusion rule. We expect that this is related to equivariant K-theory of the moduli space. But for R matrix and F matrix, the geometric interpretation is not known. So, but one can check the dictionary, especially the dictionary for fixed points, between fixed point and simple objects, and the value of the moment map for many theories. So as mentioned, class of them is given by a pair of ADE thinking diagrams. So there is a family that corresponds to A1, A2. There's a family that corresponds to A1, D, 2n plus 1. And then another family corresponding to A1, D2n. And A1A, 2n plus 1. So the Coulomb branch of this has some hidden MTC encoded, and they are MTCs associated with some vertex operator algebras. So the relevant vertex operator algebra will be denoted by chi t, and for this case, it will be 2, 2n plus 3 minimum model, Virasoro minimum model. For the second case, it will be affine Lie algebra, affine Kazmudi, at admissible level, SL2 at level -2 plus 2 over 2n plus 1. And for A1 D2n series, this will be a Wn algebra obtained by performing non-regular quantum Hamiltonian reduction of SLN plus 1 at level, I wonder whether this is still visible, n minus 1 square over n. For the last one, the relevant view A is sometimes denoted as B in algebra, Bn plus 2 algebra. And this is obtained by performing a subregular quantum Hamiltonian reduction of, again, SL n plus 1, but at a different level, minus, well, it should be lowercase n squared over n plus 1. And then the value of f for them will be respectively 2n plus 3, 2n plus 1, n, and n plus 2. And the fixed points number of fixed points, or equivalently, number of simple objects in the model tensor categories. Well, the number does not depend on gamma. So let's say number of simple objects for CT gamma equals 1 will be n plus 1. This is maybe somewhat familiar for minimum model. And 2n plus 1 for this SL2 at admissible level that Thomas has mentioned yesterday, and n squared in this case for this particular WN algebra, and n plus 2 times n plus 1 over 2 for Bn plus 2 algebra. So there, one can check that the number of fixed points, while the fixed points, there's a correspondence between fixed point and simple objects. And one can also check the eigenvalue of the T matrix with, and compare that with the value of the moment map. So let me try to get a little bit more space. So let me, so since in the first lecture, we talked about 2D theories, and now we're talking about 4D theory. Let me end by providing a big picture using 6D theory. These are going to be 6D 2,0 theory, and we will use this to put together the two-dimensional TQFT that we talked about and 3D TQFT. So for 6D theory, you can consider that on 3 manifolds times a Riemann surface times S1. And you can choose a background so that it is topological. along both M3 times sigma. In fact, you can view this as you can replace M3 times sigma with a more general 5 manifolds, and it will be a 5D topological theory. But again, some of the partition function might not be well defined. And then you can specialize M3 to be length space LK, 1. And then this geometric setup leads to the equivariant linear algebra that I described in the lecture. But if instead you leave M3 to be arbitrary and consider fixing sigma to be CP1 plus some poles, higher order poles, then one get 3D TQFT on the 3 manifolds. So the 2D TQFT and 3D TQFT that are obtained from Coulomb branch can be put together in this way and should be viewed as some specialization of a 5D TQFT. And it will be certainly interesting to better understand this 5D story. And also you see that we are considering only some special cases. So there should be more general possibilities. For example, if instead we're not having CP1 with higher order poles, but something more general, some of the dictionaries that I mentioned still work. But you want to relax the condition of having more than 10 category to something with less structure, like braided tensor category. And then there is still some nice correspondence between fixed points and simple objects, or some particular nice objects in the braided tensor category. So let me just maybe end with this following example. For example, if you take G to be SU2 and sigma to be a sphere with 4 holes, but you only have regular singularity. Then the moduli space is still 1 hyperkähler dimensional, and the singular fiber looks like the affine D4 thinking diagram. And the U1 fixed points consists of 4 isolated fixed points, and then the entire CP1. And they nicely correspond to the 5 highest weight modules of SO8 at level -2 in the category O. And there are many more possibilities, both in dimension 1, hyperkähler dimension 1 or higher. And it seems that there is an interesting, rich story that can be explored. So sorry for running a little bit over time, and thank you all for attending this lecture.
Thank you very much. Are there any questions, comments?
So this is Victor Ostrick. May I ask you a question? So you have this conjectural family of modular tensor categories. Do you expect this kind of to be modular categories that we already know, or maybe some new might appear? I mean, is there any idea?
So I think for complicated theories, in general, it should lead to something that is new. For very large class of theories, you are actually obtaining various kind of W algebra, and there is something that is known. So to maybe give an example, for like AK minus 1, A and minus 1, so this is a two-parameter family, and as long as they are co-prime, you have, well, a minimum model, K comma M plus K, minimum model. For the WK algebra. So there you can also check this dictionary between fixed points and modules. But there are many exotic theories that are not so well understood physically. And I would guess that for some of them, for many of them, it should lead to interesting VOAs and also interesting model tensor categories, not necessarily known.
Yeah, it would be kind of interesting to isolate smallest potentially exotic examples, just to start looking at this.
Yeah.
Yes, and please, can I ask, so what is the logical way? You first you have some topological side and you find fixed point, yes?
Yeah.
And fixed point, at least these fixed points are corresponding to the object of a category which you are talking, yes?
Yeah, that's right.
Next, it has to be some way to find what? S matrix.
S and T matrices.
S and T matrices, they are encoded by something. So surely,
yeah, some geometric data.
We do not understand much. Maybe Seryoja tomorrow, Gukov explained us something. But anyway, suppose it is, maybe you give some hint how to find this S matrix or something like that. But suppose the T matrix is diagonal in this basis, and diagonal element are something, the value of some Lagrangian, and I do not know what.
Value of some moment map, yes. There is some function on the model space. You just specify the function to the fixed point. Yes.
And S matrix is something more complicated. What is the way to find? But before that, suppose you know S matrix. After that, you can guess about conformal field series. So
yeah, that's right.
And it is how we are doing it. But suppose you are it is answer that it is 2-5 theory. So from the point of view, you have two objects and you calculate by some way this S matrix. Yes, and how you know about that this is 2-5? Is it some way to see it? Why it is this, or maybe it can be something else, but with the same tensor category. Who knows?
Right. So it could be something else with the same tensor category. So, but there's another connection between quantum field theory and a VOA. So for any superconformal theory T, there's a construction by Beam, Rastali, and others, leading to a VOA. And in the case of A1, A2 theory, the VOA can be constructed to be 2,5 with a solar minimum model.
So then, it means that it is some way to calculate, for example, the characters. Yes.
Yeah, exactly. One can compute. Well, one can do slightly better. So one can compute the vacuum character, but also in some cases one can explicitly find the VOA there's a physical construction. But then for this view A, you certainly expect that the relevant model tensor category is exactly this one.
So it means it's two sides. Well, one side you can try to associate three-dimensional theory, like Witten-Rajansky, where some invariants of something, knots, manifolds, and so on.
Yeah.
Or conformal field theory, yes. And this is related things, or
so first of all, the 4D theory itself is super conformal. But then this theory can be used to define for you a Rosansky-Witten model, which is like a topological but has some yield-defined partition function. So one is like the descendant of the other.
No, but and again, your dictionary are rather complicated. So it means that from vertex operator side, you have some rather subtle construction. I mean, you have very specific cassettes and so on, and some kind of guessing work where you can see it. No, it's very impressive, but I cannot imagine how it is possible to do.
So at least the dictionary involving like fixed points and this moment map values are not so complicated, right? And once you have the S and T matrices, you only have finite many MTC. So, but indeed, this dictionary from theory to VOA is non-trivial. So many people are working on this from either physics side or mathematical side. For example, Tomiyuki Arakawa has done many interesting work on this.
Yeah, but I think maybe if you don't mind, I'll interject that this connection between VOAs and MTCs in general is not known because it's like 4D symplectic duality, which does not,
exactly.
Right? And I think that's precisely what the very hard, complicated ingredient that confused Boris and maybe others. That connection between geometry and MTC is easy, as you say, just moment maps and geometry. So maybe it's worth emphasizing that that part is not complicated or ambiguous.
Yeah, so for the view A, it's more closely related to the Higgs branch. And but our story is about the Coulomb branch. And one expect that Coulomb branch and Higgs branch kind of know each other, but not perfectly. So there's a story about 3D mirror symmetry or 3D symplectic duality. And that's about 3D equals 4 theory. But the current relation discussed is like an analog of that in 4 dimensions. So one can perhaps describe this relation between this view A and this model tensor category as some sort of 4D symplectic duality. And as Sergey emphasized, this is quite a mysterious connection. And I certainly think that it worth further exploration.
Oh, I see. Thank you. Yes.
Okay. Other questions?
Sorry, probably I didn't understand the very beginning when you explained the relation between Hitchin system and flat connections and how this parameter T appeared. So when you replaced counting of sections of L to the K on CP3 by some another series involving T. So what was the geometric background? So when you didn't have T, you had like flat connections and had modular space of flat connections and have determinant bundle for corresponding connection, say, or Dirac operator with this connection. And so how these flat connections are related to Hitchin system and how T appears?
So the model space of solution to Hitchin equations is can be identified with the model space of flat GC connections on the Riemann surface sigma.
So the difference is complexification, yes?
Yeah, so the model space of flat G connections can be viewed as a real locus inside this space of complex connections. In the case of this familiar example of genus 2, this equals to CP3, and this is roughly T star CP3, but with some additional thing glued to it. For example, you certainly want to incorporate this 16 additional fixed points and their downwards Morse flows, etc. You want to glue something.
But it is still not compact, yes?
It's still not compact because the base of the vibration is non-compact. So, but what happens that this U1 action has compact fixed points, and you can use this to regularize. So let's just maybe look at the base. So if you're just having a C, and you're looking at complex functions, homomorphic function of C. So they are like, well, you have 1, Z squared, being a basis in this space. It's infinite dimensional, but then you can sum them up. Well, instead of computing naively the dimension of this space, instead of writing 1 plus 1 plus 1 dot dot dot, you can compute the character of a U1 action that acts on Z in well, with weight 1. So instead, you want to actually you can regularize that to a nice rational function. So this is basically how you can make this infinite dimensional thing. Well, you can get some nice, well-defined formula out of it.
And what replaces O of 1, which was determinant bundle in case of CP3? What replaces it here? So
there is a similar determinant bundle over that will restrict to, so there is L on this model space of Higgs bundles that will become O of 1 if you restrict to the CP3. So I didn't get a chance to carefully define this. So, but there's a natural thing that can be defined.
And the infinite number of sections is related to non-compactness of the manifold, yes?
Yeah, exactly.
And just to ask, you said that this U1 appears in superconformal theories. For example, in SU2 theory with enough matter. And said that the fixed points are somehow related to superconformal fixed points or something like this.
Yeah, so what I didn't mention is that the base of this vibration, B, can be identified with 4D Coulomb branch, or Coulomb branch on R4. So, and then there is a particular point that is singular. And if your theory is at that point, that's like the theory really enjoys superconformal symmetry.
can I say that this U1 action is somehow related to RG flow or something like this, or this is different beast?
Well, it's kind of related. So you can complexify the U1 to be a C star action. It won't be an isometry. It will change the metric, and that's actually related to a scaling behavior of the quantum field theory.
And for example, in case of SU2 theory with matter, is this a point where masses are 0 or infinity or something like this?
So to get conformal theory, you can consider the SU2 with, it will be actually exactly this theory. It's sometimes referred to as NF equal to 4 theory. NF describe amount of matter. NF equal to 4 make the theory conformal. And this is what the Coulomb branch would look like. And then you can turn on various parameters in the theory. Indeed, some of the parameters correspond to mass of the theory and mass of this matter. If you turn on this mass, in general, you will deform this into, I think, maybe 6 I1 singularities. And then you will lose superconformal invariance or this U1 isometry.
So this is a point where Seiberg-Witten curve have some additional symmetry or not?
Seiberg-Witten curve itself may not enjoy this symmetry, but well, the symmetry acts on many things. For example, parameters of Seiberg-Witten curve enjoy action of this symmetry, and for some special parameters, they are fixed by this symmetry. And for example, mass parameters would enjoy an action of the symmetry, but you want a mass with 0 to have this.
Understand. I ask this fixed point. This is a point of special symmetry of this curve, or
well, they are special parameters.
Yeah, I understand. But when I put parameters in special points, I can have some. For example, all masses are equal, or something like this.
Well, in these cases, all masses are set to 0.
Okay, thank you.
Okay. Other questions, comments? So then thank you very much for the lecture. Thank the speaker. Okay, so we resume at 8:30 in half an hour. So let me announce once more. Tomorrow at 6 p.m. We'll have a discussion session by Sergei Gukov and Boris Fagin, and everybody else is also welcome to contribute and participate and contribute. So, okay, now we have a break.
Maybe it will be some discussion we heard today, rather mysterious things, and they will be, but maybe they deserve some discussion early. Okay.
Okay. And can I also ask you to send me the notes from your lectures?
Yeah, sure.
Thank you very much. And I put them on the website.
Yeah, no problem. Thanks.
Thank you.
Thank you very much.
Thank you.